talking about various kinds of loads. And then we're going to drop into power plant instrumentation. Next. So I have our last slide is we were talking about derating. We talked about lights and heaters. I think that's where we ended, right about there. We're talking about derating switches, and then the other side of inrush current, when you turn a circuit on, typically most circuits, the high current users are going to be motors and lights. Those are both going to have pretty high rates of current coming in. The other thing that's going to happen is once they're under a load, you go to turn them off, that current's not going to want to stop because the circuit is primarily an inductive circuit. So because of that, we're going to try and do some things, particularly on very high powered circuits like a starter circuit or a master circuit where you have a large inductive switch, large inductive relay. The little bitty key switch for the starter or for the master switch, every time you turn that off, if the inductive relay tries to collapse its magnetic field, you create an arc going across that switch, that little bitty switch, control switch. It's not going to last very long. So oftentimes we'll put a little diode in line somewhere or a resistor to try and address that collapse or that additional or that desire for the current to keep going and arc the switch. We want to prevent it from arcing the switch. Okay, so other load devices. Sort of other than motors and lights, kind of probably the next biggest group are going to be communication devices of some kind, something that processes data, right? So whether it's an electronic flight information system, an engine management system, a nav radio, a communication radio, data management system, onboard radar. All of these things can use a fair amount of power, but probably, I guess, another factor in this is, along with motors and lights, these guys are going to be rated in some type of power consumption value. It's probably going to be volts and amps. Typically, light bulbs, as far as I know, as a group, are the only thing that are directly rated in power. They'll say it's a 21 watt or 60 watt or 100 watt bulb. They'll then also tell you what voltage it's designed to operate at. That's sort of a departure from the norm. All other components out there are rated in volts and amps, for which you could get to the power fairly easily just by multiplying them. But so, for example, this generator data plate right here gives you a nice speed range. Bottom speed range 1750, meaning below that it probably doesn't generate very much power. Also says its rating is 25 amps, and it's a 24 volt DC generator. So all the data you need about how much power it puts out is right there, as well as operating speed. And then what isn't stuck on this particular label yet is the actual part number and serial number, a unique identifier. This is one of those places you guys sort of need to get a little bit comfortable with looking for. The reason being is, if this information isn't correctly filled out on this component as installed in an airplane, and you inspect it and say the airplane's airworthy, it isn't airworthy if that data plate isn't there or isn't right. And I've seen this numerous times, actually. Most of the time what happens is the darn thing falls off. Well, what does Part 45 say about data marking? Data plate marking. Generally, it says must be affixed in a permanent manner. So, yeah, some of this stuff gets funky and fails. Other times it's made out of aluminum. I'm sort of okay with it. Oftentimes, like on engines, they'll want the data plate to be stainless steel, fireproof, even though it's attached to something that's aluminum. Well, aluminum can burn, but they'll still, at the end of the day, once the fire's out, they'll still be able to find the data plate for the engine that's stainless steel and somewhat readable because it's permanently embossed into the stainless steel plate. Actually, the other thing you'll often find on an engine, at least in an airliner, is a stainless steel plate that says property of Bank of America or Chase Manhattan, or because a lot of times the engines aren't directly owned by the airlines, but the actual owner wants to make sure that they are able to recoup their losses in the event of catastrophic failure.
Does a class signify like how well the or what does that mean exactly?
Say, I didn't quite hear you.
Like class and grade, is that going to tell you the quality of the generator, or what is it?
You know, I don't know what they mean by those two values. That may be internal to AC Delco's specification. So in other words, AC Delco has a whole bunch of different types, class, grade, product line. It may not mean anything engineering wise to us. All right. Okay, so it is not uncommon to see radios needing about 5 to 8 amps in today's world. In the old world, 40 amps, 50 amps, and they were like, 5-watt amplifiers. They were pretty terrible. They also ran really hot, a lot of big vacuum tubes. But New World stuff, in transmit mode, they might hit 8 amps. If they're putting out at 150 watts, something like that. The problem with many NavCom type components or devices is that they oftentimes they'll do a sort of, for lack of a better word, a redundancy thing, where they'll call upon multiple power supplies on multiple grounds. And then, of course, oftentimes you'll see them say, all right, run off for one circuit breaker with these 2 wires over to the unit. And that can be a little confusing because it depends on the unit. If it's a combined unit, like for example, the Garmin 430s and 530s, they have 2 power leads for the radio, 2 ground leads, 2 power leads for the nav side, as well as additional power leads for other elements within the unit, as well as some power outs coming off of the unit. So you oftentimes will have to do a pretty significant dive into the installation manual to get very specific information about what each wire needs in terms of circuit protection and wire size. The installation manual for an avionics component that meets a TSO usually stands on its own, and then you install it either through FAA Form 337 and or somebody out there may have engineering data as well, or if you're operating under your radio repair station license, you yourself may be certified to produce the or to use that data as the authority for installing it. So again, you kind of got to rely on the manufacturer for that. Barring none of that, well, I think anymore on any new component, I would be dumbfounded that you could buy something that didn't include that information for you. But you can then rely on 4313 as an acceptable practice. Well, in this case, it would be 2 Bravo, right? Because you're altering, you're not maintaining. The 4313 2 Bravo, acceptable methods and practices for altering an aircraft, right? Okay. And I think we've talked about this in the past, but
Good question. Seems like there's more damage that can be caused during the shutdown more than the start, right? Because of the inductance, the coils collapsing.
so yes, but more the damage is probably most likely going to come from a very large motor that typically gets used at the very onset of the use of the airplane, i.e. your starter motor. So that would be one thing you'd want to avoid, having other things turned on. Many other motors, I think it sort of depends on what the motor represents, or the coil, let me say it more appropriately, the coil represents as a percentage of the total load.
Mm-hmm.
If I've got a large battery and a whole bunch of other loads on there, and it's a small little motor that comes off and on, the rest of the loads in the battery are going to absorb any surges pretty effectively. On the other hand, all the avionics combined add up to 45 amps, and the starter puts out 400 amps. Okay, now you've got, it's like an order of magnitude bigger, and when that thing shuts off, anything that's attached to it might absorb some of that kapoof, that magnetic field collapsing off of that 400 amps as it shuts down. So yeah, typically the off is worse than the on, but
sure.
The other side of that is, and where the on can be problematic, is we don't really know what the power source can put out relative to the initial inrush current. So if I've got a fairly small cold cranking amp battery, let's say, and I hit it with the starter, what's going to happen to the voltage? It can't put out that much because the cold cranking amp is pretty low. So when I first come on, let's say the cold cranking amps is 300 amps, the starter is 300 amps, but that inrush current took it up to 700 amps. So initially that battery would drop all the way down to, 1 volt or half a volt for a few thousandths of a second until the inrush current starts changing. Okay, then it's going to come surging back up. So now you may end up with, an onset surge.
Okay.
We don't really know. What we do know is, as the manufacturer of all of these avionics, I'm going to want to make darn sure that my power supply can filter for that, and not and do its best to prevent any damage. Because the last thing in the world I want is this thing costs $12,000, and every time I start my engine, it dies. Okay, I don't care how good the product is, you're not going to get a lot of people buying your product if that's the case. Okay. One of the big advantages of the world of digital electronics has been the development of power supplies. And in fact, we have a lot of companies now that produce universal power supplies. We certainly see this in the world of computers, right? All your desktop computers, they've all got the same funny little box in there. Plug AC into it, it's got 4 or 5 connectors that stick out and will attach to most components in a standard desktop. So it's a pretty universal power supply. That's somewhat true inside these components as well. Well, they themselves may not have an off-the-shelf built power supply. They're going to have built it to off-the-shelf specs. They're going to have made some capacity for it to handle a variety of different input voltages. Now, in the case of aviation, we really only have 2 input voltages for our basic DC stuff, 12 volts and 24 volts. Even the big airliners, 737s, etc., they have a 24-volt bus. They also have the 110 volt or 115 volt bus, but Their starters run, if they run, well, I know 737s use a 24-volt starter. So, from the manufacturer's end of a component, it makes sense to design something that can handle anything from 10 to 33 volts. Now, if you look at an older world thing, like for example, you look at the autopilot out there on the autopilot's test stand. On the back of one of the main modules, there's a little switch on the back side that says it's like 15 volts and 30 volts. And in fact, the way they've got it configured is there's a little plate that goes over it. On one side, it says 30 volts, and that's screwed in place, forcing the switch into one position. If you unscrew that little plate, turn it over, move the switch, put it back in, it then kicks it down to 15 volts. They put that extra plate in there just so somebody doesn't accidentally bump the darn thing. Why did they do that? Well, probably because if it was in a 15-volt system or it was in a 30-volt system and somebody bumped it down to 15 volts and then it got turned on again, it would damage things. Well, it makes a whole lot more sense just to make a universal power supply that it doesn't matter what the voltage input is, up to 33 volts. They often will do a yeoman's job of surviving and working below 10 volts. They might get to like 9.3 or 9.4 and say, warning, Will Robinson, danger, danger, right? And then something below that, they're going to say, sorry, we're going to fade out on you or give you the gray screen of death or whatever. Somehow or another, it's going to try to work in as much as it can, but typically, as long as you feed it that value, anywhere from 10 to 33 volts, it'll figure out what it is and work accordingly. That said, if I have a fixed amount of power and I change the voltage, don't I also have to accommodate for a change in current?
Yes.
Yeah, basic Ohm's law. So if I double the voltage, I'm going to half the current. Or conversely, going the other way, going from 24 to 12, if I go to half the voltage, I have to double the current. Now, if I'm doubling the current, that might mean installing this wide-angle thunder bearing in a 24-volt system would require different wiring than installing it in a 12-volt system. It's one of the reasons why the FAA does not certify components for installations in airplanes. They build them typically to a TSO or some performance spec. And then requirements for installation in a specific aircraft are met through either field approvals or supplemental type certificates. Okay? All right. The upside of all of this new fancy, newfangled stuff is it does a whole lot more with a whole lot less weight and a whole lot less power consumption. Almost always when you go to upgrade avionics, unless you're right there keeping up with the, keeping up with the Joneses and all the whistles and bells, almost always when you upgrade to new avionics, even though you might expand features, you are generally going to be reducing the amount of current the generator has to produce. You also oftentimes will be making the airplane lighter. So I think I talked about this already, but you may need to account for additional heat. So for example, if you look at a typical radio stack, see how these guys are stacked really tightly next to each other? They can be built up that way. There might be a little bit of an advantage to like doubling that space just a little bit. The other thing is to try and use components, particularly if the components that you have that have the ability to attach a cooling fan, mount those in the middle. Okay. So, for example, this guy right here that has a fitting right there for a cooling fan, you'd want to put that one in the middle and maybe another one in the middle, and the ones out on the ends that maybe don't do cooling, like maybe an audio panel or a transponder or something like that. You could hopefully rely on some of the cooling coming from the interior units to force some air through there.
Do they ever use, do they use outside air, or is that thing?
No, it just takes air from inside behind the panel, somewhere forward of the panel, somewhere, and blows some air. It's just, what it's gonna do is just rely on air being blown. May not be the coolest of air. That said, I can tell you I know of at least one airplane, mine, that has, I did take some outside air and just fed it up into that, you know, because a lot of times what happens in the instrument panel is it sits here, and then there's a nice big round turtle deck or forward deck over it. So you now have this sort of big bowl sitting over where a bunch of heat has gone up into, and it's risen up in there, and it just stays nice and hot. Plus you got the sun beating down on it. Plus you may have painted it black to reduce the amount of glare on you. So this whole thing is a recipe for getting pretty hot. So yeah, having an outside vent that shoots a little shot of air up in there just to blow the cool air out isn't a bad idea. The one gotcha though is if you're in rain, you've got to make sure it doesn't shoot water up there, because that wouldn't be good for any of your avionics. Okay. Oh, so yeah, there's another example of a stack of trays all put together into one complete unit. Does make it structurally stronger. It also actually makes it a little bit easier to install it if you've got the capacity to do that. Install it and work on it, because then the whole thing comes out as one piece. However, that then means all of your wiring, antenna wiring, power wiring, data wiring, everything else needs to have enough of a service loop that you can feed the thing out enough to get back behind there, turn it a little bit, get back behind there, to get your screwdriver or whatever you need to disconnect the connectors in the back of the tray and get it all out of the way. Otherwise, we're going to be throwing you underneath the yoke system with your head banging against the pedals, and we may or may not take the seats out just because you should be miserable if you're having to do this. Obviously, then also routing of wires should be considered carefully. All power gets separated from all data. So data includes antennas, which are separated from any other data, which would be audio and comm and microphone and all that. And power, all separated through different routings, different bend radii, et cetera, et cetera. Yeah, so this shows some of the different connector assemblies. Note, there's a fitting for a blower, a cooler, another fitting right here. Most of these seem to have 90-degree fittings for the antenna, so that the antenna doesn't have to come straight out the back. Whereas if you look at the Garmin assembly, I know that's a Garmin right there, that plate, it's got a fitting for cooling, but the antennas come out straight as do the coaxial connectors. So in this case, if this unit is, say, 12 inches deep, I'm going to need another 3 inches or so behind there to be able to pull these cables out and gently make a turn. These not so bad because I can turn them tighter. That hose is going to need a little bit of a gentle turn. And again, all the coaxials will be needing a little bit more of a gentle turn as well. The upside of these kinds of assemblies is not only can you disconnect the connectors from here, but this whole back plate can actually be fairly easily unscrewed from the whole tray assembly. Now, figuring out what it takes to do that sometimes isn't that easy, but whereas you can see these guys, that's all spot welded together, so you're not going to be able to take that apart too much.
It probably goes down. Can you back that up for a second?
Could you, this sounds like maybe a silly question, but when you're connecting all the wires from the machine, where do they all go to the power source?
Where do they all go? To the power source. That's, you lost me.
Well, they just
Like, for
gonna
example,
feed down to the battery, the bus.
Where do all those go?
Yeah.
It depends on where they need to go. So some of them are going to go maybe over to another indicator head. Many of them are going to go down a channel and a conduit out to your audio panel, or if that is the audio panel, from there out to all the jacks for your headphones, microphones, etc.
Okay.
Some of them are going to route like the black and red ones. Those are going to. I'm going to say that's a Garmin 430 tray. I might be wrong, but it looks like it. You're going to have these two going to your power and ground buses, your blacks and reds. So some of them will go off to an indicator head if you have an OBS or a GPS indicator on it.
I guess my question was more of the power. Where from when it all has to go back to the power, how is it connected? That's all. And you're saying it's connected through a bus bar.
Well, it probably goes to a power distribution bus. So
Okay,
there'll be a power distribution bus coming off the master relay
Yeah.
to a power bar. Then, and that's going to be hopefully fairly close to each other.
Right.
Or there'll be one big lead that runs at the batteries in the back somewhere with the master relay right by the battery.
Okay.
Up to the bus. Then it'll come off that bus straight to a circuit breaker close by. And then from the circuit breaker, it'll come up to be those two wires. As well, there'll be a ground distribution bus somewhere that all the ground wires go to. And if it's done well, you'll have several ground buses. One ground bus will be ground planes strictly for your communications stuff, microphones and that type of thing. That's fairly well isolated from everything else.
All those other connectors with the wiring, once they're connected with the wiring, be set on top of it, or how?
Well, no. So what you're going to want to do is leave that there, but your coaxial cables for the different antennas, those you're going to want to route out and keep them as far away from here as possible. So you're going to want to route them the other way, or if you have to come this way, keep them quite a distance as far away from everything else as you can. You definitely want to keep that stuff separated. Now, what I don't know, looks like they've got a number of shielded wires in here. I don't know what those are. I don't know if those are audio in and outs. The Garmin 430, I think it has a 25 pin, a 36 pin, and there may be one other.
Installation.
The 530 has got some more stuff on it. So I mean,
Wire. So
you
have
could spend many
stack.
hours just building up the harness for one of these guys.
So there's those wires coming, and that stack will be back here. So they'll move the wires down and the bus bar.
And also note,
they'll go down.
well, these guys had connectors.
Mhm.
These guys already had a short stub out
And up to the
of
circular
wire
panel.
for the antenna
Right.
that then has a connector. A little hard to see. It's sitting right there. That looks just like that. It's the female version of the BNC.
Bus bar to put it,
And
and the speakers and where they can go.
So the BNC connector that you guys are playing with in lab, that's what you're going to attach to the back of that thing. You'll either attach, I guess it's right here. You'll attach it to this, or you'll attach it onto one of these. And so let's see, you're going on the 430, you're going to have the glide slope, the ILS, and the comm radio, I presume. And then somewhere, actually no, one of these serial lines will be your line in from the GPS antenna. There may be one more. Marker beacon?
But you can see
The
there
marker
are a
beacon?
bunch of wires.
That's for
bunch
the
of
audio
wires
panel.
and
Trying to
they
remember
have-
what
they
the
have to
fourth
go
one
to
is.
different
I'm
locations.
curious how. I wonder if we go into the box. I wonder if that can show us.
Yeah, that'd be cool.
So you have your nav, ILS.
GPS and comm.
Didn't think the GPS was a BNC.
TNC.
That's TNC. Okay. Well, maybe this is a TNC down here. I can't quite see it that well.
I know that there are TNCs on the, I don't know if they are on the 430s.
Yeah,
But
it's-
they are on the 650s.
Right. All the newer ones use the TNC for the GPS, but I don't remember what the fourth one is. I remember going through this installing a 430, but
Is that backplate then established, so now the radio is just gonna go down
No.
and try and hook up?
well, yes, the radio will go into and run into all of these things
From the other side?
from the other side,
other
correct.
direction.
Same thing true here. You don't actually see the connector in here. The connectors have been physically removed from each one of these. So essentially, if you build up a tray, what can happen is all the trays are one piece. you pull it out, you get back behind there with a screwdriver working from either side, and you can remove all the connectors from this assembly. Or in this case, you can remove the whole back plate from this assembly so that now the trays are out of the way. You've already pulled the radios out. The radios pop right out. Like a 7/64 or smaller Allen wrench, 5/32. Allen wrench pops them out. Okay.
Are you gonna show a picture of like when it goes into the circuit box?
I'm not going to go too deep into that because it's more for the airframe class. Avionics, just teasing you here.
You got a picture of that if you want.
But you can look it up. Yeah, I mean, it's just
Yeah, I
online.
was just curious.
So, all right, so it's probably not a good idea to take any of these high current wires and run it around any flux gates, electronic compasses, magnetic compasses, any other device that will be disrupted by the addition of magnetic fields anywhere nearby. And a lot of times these guys, they're pretty critical. So for example, electromagnetic compasses used in many components, the Dynon components, GRT, Shelton, etc. They're like nothing iron or electrical within 12 inches. I mean, nothing. No, well, it's kind of hard to find a box that big in an airplane that doesn't have any iron or any electricity. And then, of course, almost always, once you install it, then it has to be certified, tested, and verified to be operationally correct. The last thing is, if you're going to do any kind of electrical installation on an airplane, almost always going to be a major alteration. And the definition of whether it is a major alteration or not is somewhat subject to the local inspector, FAA inspector. I've talked to a lot of inspectors over the years. I've seen some of them be so anal as to say, if it's a suction cup and it's plugged in with a cigarette lighter, it's a major alteration. That's a little over the top. You know, certainly if you're going to be cutting, hacking, crimping, connecting wires, all of that kind of stuff, there's a pretty good likelihood that most inspectors are going to consider it to be a major alteration. In which case, if you're not a radio shop, you're just sort of doing this on your own, you probably want to talk with somebody at the local FSDO before you cut, hack, crimp, grind, or otherwise alter the airplane. Now, what's a little difficult in this is there's a lot of stuff that our local FSDOs aren't authorized to certify anymore at the major alteration level. They're not, you know, so it's, you got to ask, but it's very likely they're going to say, yeah, it's got to go back to Oak City. And again, their perspective is they want to see you ask first. Do the paperwork first before you start modifying the airplane. That's not a good place to be.
It's relatively lax in San Diego. It's relatively lax in San Diego. Like GC 155, they don't consider that a major alteration.
Yeah, San Diego, and it's funny because 25 years ago that wasn't true about San Diego, but now they seem to be a little bit better. I've heard some complaints coming out of the Bay Area that they some you know, staff changes and they suddenly, or somebody got in trouble. You know, somebody said yes, and then something went wrong, and no good deed goes unpunished. So then they just tightened it up and started saying no to everything. We don't really know historically. Part of the reason stuff is being kicked back to Oak City more and more now is because at the national level, and I've been in the room watching them take flack for it. At the national level, there are a lot of folks that are sort of beating the FAA up and say, hey, look, I go over to this FSDO in this region and they say this is okay, but over here the same exact thing, they say it's not okay. Of course, at the national level, they're going to say, yeah, we kind of got to be consistent. At least at, you know, at the basic level, we got to be consistent. On the other hand, I agree with the idea that the local or regional operators or government agents do need to have some flexibility to be able to manage what's happening around them. So,
Oak City can't do everything. They're
Huh?
way behind. Oak City can't
Hey,
do everything.
no,
They
hey,
can't.
are you kidding me? They're so
They're
understaffed.
so buried in the bureaucracy.
Our local FISDO for the first time in 22 years is fully staffed.
I know.
For the first time.
Although we
22
still
years.
technically don't have helicopter DP. and we
I
have
know,
like DP, we don't- but, you know.
But it's
They consider it fully staffed though.
they consider themselves to be fully staffed at this point, which is better than not even considering themselves to be fully staffed. Yeah, I know. It's so, the point there really is, it's in your best interest to ask. Huh, there's something in my mouth. At the very least, they say, it's no big deal, go for it. And you've shown them that you're the kind of person that would rather work with them than hide something from them. Okay, that's the way to build rapport. Call them up and ask. Say, hey, this is what I'm doing. I got a buddy of mine, he's completely rebuilt a T6. He wants to do X, Y, Z. What do you think? Okay. And there is a cool little rocket engine. That would be fun to wire up, huh?
Those ones are one-time use, but what is Tesla doing that's making them reusable?
I don't know. It's like asking why are atoms. My guess is on the Tesla rockets, there's a lot that isn't reusable. There's a fair amount that is and a fair amount that isn't. I can tell you right now that these nozzles that sit in here and this whole cone, a lot of material gets eroded away from it on any rocket. So my guess is a big portion of this gets replaced even on the Tesla ones. On the other hand, stuff like this, all of this stuff out here probably is completely reusable. If you can catch it. And that's where Tesla came up with some really cool rocket Velcro. Okay? You guys see it, it comes down, it sticks. Okay, it's gotta be rocket Velcro. Right? All right, let's talk about power plant instrumentation. Where are we? Yeah. Yeah, that we've already done. Okay, this is a fairly short section. This is an area, because of electronics, that has changed dramatically. Now, what's interesting is, I'm sure some, if not all of you, have heard that they've been doing a whole lot to revise the tone and nature of Part 23, which is the certification of airframe components. I have not yet heard what they're going to do with respect to changing Part 33 and now just brain fade, the turbine part, recip part, and or certification standards for recips and certification for turbines. My guess is they're gonna do this to Part 23 and then sit back and see how it plays out. And then eventually they may come back around with Part 33 as well. The problem is, an engine system that's monitoring engine data, is it really an airframe component or a power plant component? I don't know. It's kind of gray. The FAA pretty much says it's an airframe component. They expect the airframe installer to be installing it all. I would have to say, whatever I'm bolting onto the engine directly, probably ought to be a power plant, which is going to be the sensors and the etc. So then, if I look at Part 23, which is now being changed, in fact, I think it supposedly goes into effect in June, to less of a standards-based and more of a performance operational-based specifications. Where do I start drawing the lines in terms of me as not the installer, but now the inspector, looking at this and saying, Okay, well, this has got some new fancy equipment on it. Is that equipment deemed airworthy? How do I, what's the basis by which I say it's airworthy? Of course, at the last IA seminar, Larry and I both went off on them, because they got up there and started, the FAA got up there and started spouting off about it. So I started going at chewing on them. So for example, I got this new wide angle whiz bearing, whizzy gig thing that will measure all kinds of stuff and do all kinds of electronic data recording and all kinds of really cool stuff. It's not manufactured to a TSO, so there's no data in a TSO that tells me what it takes for this to be considered airworthy. So for example, if it was electronic like this, it may well be that the manufacturer would include a statement that says something to the effect of and must include the most current software update per umpty, right? That doesn't exist because the TSO isn't required anymore to install this. Just as an IA looking at that and looking at the software, go into one of the screens and say the current version isn't what the current version the manufacturer has. Can I say this is airworthy? I'll have an answer for you. Of course, the FAA didn't have an answer for me either, because they didn't actually really understand what's happening with this thing. It was sort of one of those funny conversations. The blind, we're definitely leading the blind. All right. So we kind of have three basic categories of instrumentation systems that we use for establishing, measuring, assessing what's happening with the aircraft power plant. The first one, which is not necessarily older, but typically is the older type of technology, is mechanical technology, either hydromechanical or fluid mechanical or physical mechanical. There are within the group of mechanical, there's also electrical or electromechanical. So for example, I might be using an electrical variable resistor that changes in different conditions, but it's physically moving a mechanical gauge. And the Arsenball meter movement. Okay. Then the third group is going to be purely electronic. It'll have some electronic display that displays all of the information in a variety of different graphic ways. Analog ways that look like an analog meter, digital, or both. It'll then take primarily a bunch of analog electrical sensors, run them into its own little brain and convert them to digital data, and then once they're converted to digital data, display it in whatever manner that the manufacturer has decided is best. Now, having said that, one of the advantages of some of the electronic components is, particularly with power plant instrumentation, is they can program these things to allow you to set up a bunch of different ways of looking at data. All right, so what do we need to know some things about? Certainly we need to know various temperatures, right? Now, in an air-cooled aircraft engine, we're probably only going to really, or the most important temperature we're going to need is going to be oil temperature, right? Now, if it's also liquid cooled, we're going to want to know liquid coolant temperature as well. But we might also want to know cylinder head temperature. We might want to know exhaust gas temperatures, turbine outlet temperature, all kinds of different temperatures. There are a variety of different pressures we might want to know, like oil pressure. In fact, oil pressure kind of going to be so important that it's mandated as one of those instruments in Part 91, oil temperature, oil pressure. We might need to measure physical motion, like revolutions per minute. Okay. Might also need to be able to measure position. like cowl flap position. Might have a physical throttle position sensor. Why would a throttle position sensor be important?
Throttle position.
The
Yeah.
speed, your speed.
Throttle position.
What must you do if you pull the throttle all the way back? You must land eventually. Okay, so if you pull all the throttle all the way back, it's really likely you're going to be landing. So if the throttle's all the way back and the gear aren't down, do you want the airplane to say, "Warning, warning, Will Robinson"? Yeah, truly, about the only time you're ever going to really pull the throttle all the way back is in that landing phase. So that would be, and in this case, it might just be a physical switch connected to the throttle somehow. But that's very useful information if it can prevent an accident. Quantity, like fuel gauges or maybe oil level, rate or flow, so rate of fuel consumption, gallons per hour might be useful, or pounds per hour if it's a turbine engine. So who's going to use the data? Well, if we train them well enough, the pilots might use the data. I don't know, sometimes. You guys, as the maintenance personnel, most definitely need to be able to use the data. Now, if the system doesn't provide any kind of data logging, then operationally you may have to go operate the equipment to collect the data. You can, in some cases, get reasonable secondhand data, from a pilot or operator. Particularly if you give them a form and say, "Hey, this is the kind of, you've got this problem. Here's the data I need. Give me some more information." But I've been burned a lot of times by getting data from an operator, and the operator, sort of, they put their own perception in there. They put their own interpretation of it in there. So I warn you, take that with a grain of salt. There may be specific warning systems out there. Warning lights, like a high voltage alternator light. And then, of course, the flight management or other automated system may also provide data relevant to the problem you're having. Okay, so by and large, mechanical instrumentation is somewhat limited. We can definitely sense pressure. We typically do that either with, for higher pressures, with the bourbon tube, lower pressures with an aneroid bellows. We can also measure temperature either by a physical means of a bimetallic spring that will distort or change shape as it heats up or cools down. Another way is we could take and make an enclosed chamber that feeds a little capillary tube out to an aneroid bellows, and as you heat that chamber up or let it cool down, that will cause the aneroid bellows to deflect or expand or contract. So we can use pressure to assess temperature. We can use physical position switches to tell us where things are. And rotation, we can do rotation in a couple of different ways, which we'll talk about each of those.
Well, you said sensing pressure again. It was the aneroid.
The bourbon tube, Bourdon tube,
The Bourdon tube for high pressure.
and more sensitive pressures would be your aneroid bellows.
Aneroid bellows.
So your brass balloon, the little
Aneroid
bellows.
Do they make, I mean, sounds like a silly question. Do they make planes that mostly, like small little planes, like maybe the older ones they fix up with just the mechanical?
Oh yeah, there's hundreds of them, thousands of them out there. Theoretically, all they need is a couple of those, 3 of those.
Oh.
Tachometer, oil temperature, and oil pressure. Okay.
Something there for-
Yeah, there's hundreds, all the Piper Cubs that are out there. Okay, all the little Cessna 150s, all the Luscombs and Champs, and that little plane out the end of the hangar here is a good example. Yep. And all of that stuff, you can still buy all of these gauges in either reconditioned or new. Okay, so the more higher pressure type things, what we do is we take a little bitty curved tube. And it's a pretty stiff little brass tube. And if I start subjecting that tube to pressure on the inside, it starts trying to straighten out. And as it straightens out, it grabs the end of that little lever arm, which is your needle movement, and it starts flexing it. Okay, so as this guy starts trying to stretch out, it starts trying to go this way, causing this little bell crank to move with the little sector gear that then drives my needle. Okay, it's designed to read anything from, say, 10 or 15 psi all the way up through whatever pressure you've got. If it's something that you need some sensitivity to for in like inches of mercury or something, substantially less than 10 psi, what we're going to do is we're going to take and make a very, very thin-walled, bellowed chamber, maybe with a little spring. This may have gas in here or may be completely empty. We don't know. If we don't want it to respond to changes in temperature, then we'll leave this empty. It'll be evacuated. If we want it to respond to changes in temperature, then we'll fill it with nitrogen, usually, dry nitrogen. Then we're going to put it in a case that's sealed except for this little hole. And then as I change the pressure in here, that's going to cause that balloon to expand or contract. Again, driving a little sector gear with a small little hairspring and a little needle and a scale that is proportionally scaled accordingly. Okay.
That's pretty cool. Pretty simple.
Temperature sensing, still pretty commonly used these days. We have what's called a temperature bulb, and they made so many of these, they did this so much that they actually came up with SAE standards for these. There's a standard SAE fitting that goes in around the bulb shape, and then the bulb shape will come, the bulb will come with this big long tube completely soldered all the way up to the gauge. They're all together as one piece. You pull it out of the package and you very carefully unwind this copper tube, feed it all the way through the airplane, put a couple of loops in it, and then into the back of the engine, wrench it down, and then let's say this end is subjected to engine oil. As the engine oil starts to heat it up, the pressure starts to build up inside this little tube, and it starts stretching out a little bit, causing the pointer to move one way or the other, depending on whether it's expanding or contracting. If any part of that gets cut, compromised, leaks in any way, shape, or form, the whole thing has to be replaced. And these are typically sold as one complete unit. Okay. So position or quantity, a variety of different ways of doing this, but a lot of times we'll use an electrical switch. We could be so simple as like the Piper J3 Cub forward tank fuel indicator. The small little piece of aluminum rod with stuck on the end of a cork. So the tank is full, the little rod sticks up right out in front of you. It's about as simple. Or you look inside at the wing root, there'll be a little lever arm with a cork and a little needle just at the root of the fuel tanks. Okay, quantity indicators. Cowl flap might be electrical switches. They might even have a cable hooked up somewhere to the cowl that then runs over inside the cockpit and drives a little arm that sits in a slot, and as that arm goes up, it tells you the cowls are closed or cowls are open. Fairly common in the old days for us to use in single engine airplanes with the engine right out in front. It's very common for us to use a tachometer gauge, a rotational rate gauge, where we had a drive cable connected to one of the drive gears on the back of the engine. And that drive cable was a flexible Belden cable that goes all the way into the instrument panel, and it spins around and around with the engine based on some SAE standard. It's typically not one-to-one. That drive cable then will either drive the cup or the magnet. It's usually the magnet. There's a rotating magnet. And as that magnet is spinning around, that starts inducing eddy currents inside the magnetic cup. Those eddy currents start trying to couple with the electromagnetic magnet spinning around and cause the cup to start trying to pull. Well, there's a coil spring keeping the needle pointed all the way to zero, but the more that magnet spins around, the more it starts dragging the cup the other direction. And that gives you some moderately accurate value for RPM. These aren't all that accurate. Another type is they actually have flyweights going out, and as the flyweights go out, they push a spring up, and that spring, as that spring goes up, it pushes a little sector gear that then drives the needle. The problem with these is, if I've got an engine out on the wing, and I'm a constellation, so from the outboard engine to the wing root, I've got 45, 50 feet, and then from the wing root all the way to the cockpit, I've got 70 feet. That's a pretty long cable spinning round and round and round. So the cable technology here isn't going to work that well. If I could come up with an electrical way of doing it, it would be better. And by the way, these cables, very high maintenance. Little cable in there spinning around at least once per every engine revolution, or maybe once per every other engine revolution. How many revolutions does an engine spin in its lifetime?
Many.
Okay, so yeah, this cable is going to be high maintenance, particularly if it's got a lot of twists and turns in it. So in electrical instrumentation, things got a little bit better. At the first level, we came up with pressure sensing. We actually just came up with a physical mechanical switch. And the physical mechanical switch could be normally open or normally closed. So in other words, when everything is off and there's no pressure, the switch could be open or the switch could be closed. We may also use the switch housing itself as part of the electrical circuit. So for example, I could take a little set of contacts I could take a little chamber, or a little chamber into here, feed oil pressure into here, have a small insulator in here, like this with the brass, let me change that, with the brass disc in here. Actually, let me curve it the other direction. With a brass disc in here, and maybe a little spring that comes down and pushes down on it. Then I'm going to have a wire come down to here with a contact right there. And when the pressure hits a certain point, it's gonna take this thing and connect it up to this contact right here and connect this wire to ground. Okay? So, or I could do it the other way, where I could do it that way, but I could make it at very, very low pressure. Or let's make it the other way. Let's say it's connected, but at low pressure, it's connected at low pressure, but at something above, say, 10 psi, it disconnects. Okay? So let's do it this way. Let's say this comes through here, and it's connected at low pressure, but at a little bit of pressure, it disconnects from there. Then what I'm going to do is I'm going to go over here, put that to a light bulb, and take that to positive on the battery. Okay? Feed oil pressure into here. Anything above 10 psi, this disconnects and your oil light goes out. Right? Anything below 10 psi, oil light comes on, says you're about to grind your engine up. Okay, that's a very fairly simple way of using a switch. That would be in the normally closed position until oil pressure gets above a certain value, and then it goes to open. Another very, very common type of pressure sensor is a carbon resistive element, where much like the carbon pile regulator, if I take this whole arrangement and just put some carbon discs in here, okay, and have my lead come into there, and then the bottom end of it is attached to there. So now if I feed pressure into here, it starts to compress that set of discs. And as they compress, their resistance changes. So now I've got an analog device, more than just on-off. Okay, the more pressure I get, the less resistance I get. So now I'm going to set that up to run my Darson ball movement. And so you can see this here squeezing. As the pressure squeezes it, the voltage being allowed across increases because the resistance drops. A third one is what's called piezoelectric strain gauges. What those do is, I'm not going to dive too deep into piezo crystals, but piezo crystals are voltage generators. And as you strain them from their natural relaxed crystal state, they start causing current being transmitted across one polarity to change direction, and on a different axis, you'll start measuring voltage. The more you strain it, the more voltage you sense. These guys are so sensitive that I can actually make a 5-axis or 6-axis piezo crystal that I can use as a G meter that will measure down to 1/1000th of a G. In fact, I can buy the entire circuit that's completely set up, one little chip, does it all, and it provides digital data out. You don't have to do anything other than glue the chip on and give it voltage and read the data coming out, down to 1/1000th of a G. I know because I got TI, Texas Instruments, to send me a couple for free and made a cool little G meter out of it. And actually one of the problems I had was writing code. It was way too sensitive. way, way too sensitive. So I had to write code to get it to desensitize the data. Another one that's a piezo sensor. This one right here, that's actually a standard automotive map sensor being used to measure manifold absolute pressure. Feed it 5 volts and ground, and it feeds you electronic digital data, a 0 to 5 volt scale for manifold absolute pressure. You then take that voltage and feed it into your computer, and then it'll do something. I really shouldn't say. Well, so yes, you can use the you can use a 3-phase AC or DC system to create how do I want to say this? variances in the three-phase meter movement. So as physical load gets put on whatever the contact arm is, that's going to cause the three wires in the in the unit to distort, where current will be, instead of having three balanced fields of current, one of them is going to be less and the other two will start to gain proportionally. You can then use that to drive a divorce involved movement. So that's a whole other way of measuring pressure. Not used, it's kind of complex. Not used that much, but at least anymore. Now, temperature, electrical temperature measurements, this is probably the first place where we saw the use of a lot of electrical gauges being put in airplanes and automobiles and everything else. There's really two categories. The first one is, it turns out carbon, pretty much any variety, like the carbon resistor, which isn't too dissimilar from a charcoal briquette, right? It turns out that the resistance value of carbon is very sensitive to differences in temperature within certain operating ranges, okay? So from about, and I forget what it is, minus 50 degrees up to about 500 degrees, it turns out that carbon, as you heat it up, its resistance will go down. So it's a negative coefficient up to a certain point, then it starts going the other direction. So if my temperature values that I'm reading are between minus 50 to 500 degrees, then I can just take a very small piece of carbon, plug it into there. One end's connected to ground, the other end is connected to this wire, and depending on the amount of resistance being felt, I can extrapolate exactly how much temperature or how hot the end of this probe is. Pretty straightforward. A little bitty 1/8" pipe thread, screw it in there, one wire goes to there, $8 grand. It ought to work really good. The only real problem with these guys is they ground through the housing into whatever they're attached to. That means that whatever it's attached to has to actually ground somewhere. So like if it's attached to the engine actually has to ground somewhere, or it isn't going to work. So it has to ground to the same spot that the gauge grounds to. Okay? I've not had this happen once. I've had this happen multiple times, where somebody doing a really good job of cleaning all the engine parts up, and they painted and powder coated and made it look really, really nice, and put this back of the engine, all this stuff back together, and then they screw this guy in. Only the little oil housing that it's bolted to doesn't actually ground to the engine. They put enough sealant on there and everything else to where it doesn't actually ground. Well, it grounds well enough to get out the door, but then after a while, the oil temperature readings are way off. Well, pretty soon, guess what? There I am with my voltmeter, measuring voltage drop. Get a little bit of a voltage drop from here to there, but not enough. But then I go from this housing to the engine, and I get another voltage drop. And then maybe from the engine to the airplane, I get another voltage drop. Shouldn't have any voltage drop on the ground side, should I?
No.
But voltage drop is my friend to help me figure out what the problem was. I've seen that a lot of times, surprisingly. I've even seen brand new auto manufacturers do that stupid one. The second area of temperature measurement is when we're outside of that range. So if I need something that's going to be in the, say, 200, 300, all the way up through whatever, thousands of degrees, temperature monitoring, it turns out that if I have that much heat available in terms of temperature, let's say I've got 500 or 600 degrees, or 400 degrees, let's say, 350, 400 degrees. Comparing that to where my gauge is probably going to be at what, 70, 80, on a hot day, 90, okay? Cold day, 40, somewhere in there inside the cockpit. Well, it turns out that that temperature differential is enough to where if I take two dissimilar metals and I run them together in long, thin wires and join them at both ends, I'll create what's called a thermal couple. Now, specific metals, all dissimilar metals will do this, but specific metals will create a fair amount of voltage, not much current, but a fair amount of voltage in terms of sensing. It's still millivolts, but it's a fair amount in terms of being able to sense. They actually become a power generator, a battery. So I'll have a hot junction and a cold junction, and that will produce a measurable amount of current for each unique temperature differential. Now, this does mean that I'm going to introduce some inaccuracies. So my gauge on my panel might be calibrated to be accurate at 80 degrees. And the other end of this thing is stuck in the cylinder head at 380 degrees. And on a hot day, my cold junction might be a little bit warmer than normal, which means my reading is going to be a little bit lower than what I actually thought it is. Going the other direction, the differential is going to be a little bit greater, so it'll be a little bit higher. So this doesn't work too well much below about 250 degrees, because that percentage of change and the cold end is going to really skew the results quite a bit. Okay, I could still use it, but it would skew the results quite a bit. The other thing that's sort of awkward about this is I've got these two wires that, you know, one's made out of Constantine, the other's made out of iron or whatever. I've got to run them from the gauge all the way out to the airplane, to the engine, to whatever it's stuck into. Well, it turns out that these particular devices, I can cut the wires and patch a piece of copper wire in there. That's also going to form two additional hot and cold junctions, but they're going to affect equally, so they're not going to distort things too much. I will say, though, that these things, because they operate in the millivolt range, any funky connections, any corrosion, any slight distortion there, cause them to misread greatly. Now, if I've got something like exhaust gas temp, so I'm at 1800 degrees, 1900 degrees, man, that's going to work great. This thing's going to work really well. In fact, the bigger problem with it is take a couple pieces of metal and stuck them in some, stick them in some hot gases that are burning at 2000 degrees. They might not last very long. In fact, I'm going to have to shield this thing very carefully and put it in a nice package so that it doesn't get eroded away. Okay. So galvanic temperature responsive metals. So the first thing I talked about, called the thermistor, typically they're made out of carbon. And if you look at kind of what I'm doing here is, if I provide a little bit of power and I create a voltage divider here, okay, across this side, I'm going to have a very fixed amount of voltage drop between here and there. I'm going to have a constant amount of current, but these would be pretty high resistances, right? So this will be at 1 voltage. Then the voltage divider on this side will have this variable resistive element sitting in here. So this voltage will either go up or down depending on what that resistor is doing. This guy remains fixed. This guy goes up and down. So this voltage changes. This one remains fixed. Okay? So that means the voltage between the two start to change. So as they start to change, they will affect the amount of magnetism being felt on either side of these coils, causing the whole movement to want to move one way or the other. Now, in most cases, what we're going to do is we're going to balance this thing against a spring. So we're going to have a spring move it to 0. And then the more current that I drive through here, because the resistance starts going down, the more current I drive through here, the more the armature wants to move into whatever my reading value is. There are a couple of exceptions, like an amp gauge, where in an amp gauge we actually use a double wound spring and it holds it in the center. And so reverse current causes it to move one way, forward current causes it to move the other direction. If you turn off all the current, the double spring brings it back to zero. Called the arson ball movement. Very sensitive instrumentation. And this works very much the same way an electric motor does. It just, instead of spinning round and round, it just motors one way or spring load back the other direction. These guys will often, the meter movements will also often have a little disc in there with a little sort of a little bit of tension against it to cause the meter to sort of move sluggishly because you don't want it bouncing around. So this then shows the thermocouple types. This one, chromel and alumel. And then note they put some copper in here up to the meter, but inside the meter you're going to have a little piece of chromel and a little piece of alumel finishing the cold junction. Then the other thing that they did is they said, whoa, well, let's come up with different metal combinations and standardize those metal combinations. We'll color code them. And then we'll come up with names. So they came up with a J type and a K type and a whole bunch of different ones. In fact, I think the next page shows a chart. Well, the Americans did their thing. That was the thing. We know, hey, those of us over in Europe, we got to come up with our own standards, and those of us over in Japan have to come up with our own standards. In Russia, we got to come up with our own standards. But at the end of the day, you've still only got so many different metals you can play with. But they did come up with some basic color codings. It's a small amount of voltage, it's a small amount of current, but we don't need a whole lot. And the upside is it's fairly, within a given range, it's fairly consistent, fairly accurate. So CHTs, what do we typically see in cylinder head temperature?
4 degrees C.
Basically 200 to 500. Pretty much not much more than that. At 500, you're doing damage, okay? So J-type, we're going to pick a couple of metals that work pretty consistently within that range. EGT, now we're going to be more like about 800 all the way up through 2,000 degrees, somewhere in there. So we're going to pick a slightly different combination of metals. And then this guy, essentially, between this junction and the little junction that's in here, becomes a battery, producing a small amount of millivoltage that can then be measured and drive the data out or drive the meter movement. Okay, so here's an example of, so K-type is nickel chromium. For the positive leg, nickel aluminum. For the negative leg, and this is going to say, and this is in Celsius, 0 to 1100 degrees continuous. For short term, minus 180 all the way up to 1350 Celsius. That's pretty hot, Celsius wise. So if you're the European standard, those are your color codes for the wires and the outer insulation. J-type is going to be iron and copper nickel. Again, a much narrower range and lower range operating temperature. And then there's a whole bunch of different ones. What you're going to see most commonly, yellow and red, sometimes with a yellow insulator on it, is always going to be your K-type for your EGTs, and then white and red are going to be your J-type for your CHTs. In fact, exclusively. CHT and EGTs, the package, the probe, the way the probe is configured, the way it's mounted in, there'll be a bunch of different ways of doing that. Fairly commonly, the manufacturer, like Lycoming and Continental, they have a little threaded port in the head that's just a dead-end port. that you screw a little plug in, and then the temperature probe is encased, the cold or hot junction is encased in a little stainless steel adapter with a little quarter turn like a BNC connector. It just goes in there and spring loaded and clips down. For the CHT. EGT, there's a stainless steel insert with the hot junction in there, and you drill a hole in the exhaust pipe, and then that probe just sits in the exhaust pipe with a clamp going around it, holding it and sealing it in place. Okay. Yeah, so what do we got? We got European, British, American, German, French, Japanese, oh no, Russian. Well, I'm sure there's I ran out of page. This is one of those places where, yeah, you sort of see some repetition, some, but not, it's not universal. So here's a couple. This is the type where this insert right here comes off and screws into the cylinder head. You torque it down. Then this outer nut and the inner probe slide through this collar up into there, and you torque it down. This is another type that's commonly used that gives you very erroneous data. This is designed to replace the spark plug gasket. Remember the spark plug gasket that you were supposed to replace every time you pull the plug out? But apparently not with this, I don't know. Remember the spark plug that's designed to control the heating and cooling of the cylinder head? So a lot of extra heat leaves through the spark plug. So this might actually not be the temperature of the cylinder head. It's probably going to be quite a bit hotter. I do not recommend using these. Garbage, garbage, garbage. In fact, any type of gauge like Westech, oh, did I say that? Gauge system that uses those, I wouldn't consider using it on an airplane. I wouldn't use it on my lawnmower. Oftentimes, a little bitty Cessna 152, do we even need this? Maybe. If we are, and we're only going to have one gauge, we want to stick it on the hottest cylinder. Now, figuring out what the hottest cylinder is might be a little difficult, but usually it's going to be towards the back. Okay, not always, usually. You might have to start asking around and find out what the best, or ask the manufacturer, hey, I'm installing this on a, what do you think? Obviously, any turbines or anything like that, it's going to have to be certified equipment. I will tell you, monitoring EGT and CHT is one of the most important things you can do on either a turbine or a reciprocating engine to be able to monitor the health of the engine and monitor it operationally. You really want to be able to set the mixture correctly, particularly for cruise configurations. You need CHT and EGT. Absolutely. To me, it's one of those things that's like oil pressure and oil temperature. It should be required for an air-cooled engine, period. But they didn't do that. They don't listen to me. Nobody ever listens to me. Yeah, we'll do one more slide. One more on thermocouples and we'll take a break. So this shows a typical exhaust gas temperature probe. Note how the clamp, that's just a hose clamp, the hole drilled in it, and this guy is stamped into there so it can't escape. And then you drill a hole in the exhaust pipe, open the clamp up, wrap it around there, slide that in the hole and bring the clamp down tight. That'll seal up against there. So the question is, where do you put the hole?
12 o'clock.
Self-adjusting one? I don't know.
The hole is self-adjusting?
The come on. Thermocouple.
No, the thermocouple is going to be giving you literal readings of some value. The truth is, we don't really care what they are. What we care about are what are the relative values. Okay, so if I take and put it really close to the exhaust valve, I'm going to get much higher readings. However, my probe isn't going to last very long. If I put it really far away, like 15 inches away from the exhaust valve, I'm going to get much colder. When I say colder and hotter, put it right up, an inch away from the exhaust valve, I'm going to be seeing 1600 degrees. I get 12 inches away, I'm going to be seeing 1100, 1000, maybe 1200 degrees. And it's going to be less accurate. Okay? Most of the time, the instrumentation manufacturer will tell you where to put it. Sometimes that doesn't work because the exhaust system has joints and they won't be even for different cylinders. So what you've got to do is go around and look at all the cylinders and say, what's one common distance that I can physically work for all of the different cylinders? So cylinder 4 has a joint at 2 inches. Cylinder 3 has a joint at 6 inches. Cylinder 1 has a joint at 2 inches. So what's some value that I can find that will be the same for all cylinders? So that for each probe, they're exactly the same distance away from the exhaust valve. Now, operationally, the way I'm going to use this is I'll fire the engine up, warm it up, and they'll all come up to some value. Fairly close to each other if it's fuel injected, kind of not so close to each other if it's carbureted. But at that point, as I, at full rich, I go to full power, take off, they're all sitting there, and as I start to bring the mixture to lean, they'll all start going up, sort of respectively, till some point where one of them starts going down, then the next starts going down, then the next starts going down, and pretty soon one starts really going down as the engine starts misfiring. What I'll be looking for is where that sort of average peak is. And if it's fuel injected, they'll all do it pretty close to the same value, same place. That's kind of where I want to run the engine if I'm below 75% power. So if I'm cruising. At any other value above 75% power, it's not going to matter because I'm going to want to be at full rich because that's what the manufacturer says I must do. And if I'm operating for higher, I have to do it. If I just want to keep my warranty valid, I kind of ought to do it. It is a little bit of a learning curve for the pilot, but that's okay. There's a lot of great information. There's actually several really good videos about engine monitoring using EGTs out there. One done by a guy from the Bonanza Club that he did a really nice job. That's sort of very simplified so that pilots can actually understand it. But that said, you guys also need to know how this works so that when you install it, you can get the owner, operator, pilot up to speed on how they should be using this data. Okay. Let's take a break here. Let's come back.